Okay, in this particular clip, we want to address the question, why don't we just shrink the probability of a type 1 error to 0 or nearly 0? Okay, so I have a little setup here that we have to talk about. Number one, we're going back to a one-tailed test. Okay, so we're going to test the hypothesis that alpha 1 is bigger than 0, or whether it's less than or equal to 0. Okay, so we are going to reject the null hypothesis if we have an alpha 1 hat that's sufficiently large. Okay, so let's suppose that we pick the probability of a type 1 error initially to be 0.05. Then we would add up the area under the curve from this end, and when we got to the point where that area equaled 0.05, we would have computed the probability of a type 1 error. Why? Because this top distribution assumes a true value that's consistent with the null. So we're assuming the null is true, and we want the probability of rejecting the null when the null is true. So we want the probability of getting an alpha hat in here. So what's the probability that our alpha hat lies in this area? And then we want to set that probability at 0.05 and use it, thinking backwards, to identify the appropriate critical value. I've labeled it alpha C1. Okay? Now, so far, we haven't talked at all about type 2 errors. So a type 2 error would occur if we failed to reject the null. That is to say, if we drew an alpha hat in this region, also this region, okay, we failed to reject HO, but HO is false. So if we want to think about that probability-wise, we cannot look at the top. We cannot look at the top distribution, because the top distribution is centered on a value that assumes the null is true. And when we're thinking about a type 2 error, the null must be false. So we've drawn a second distribution down here that happens to be centered on a value of 2. 2 is a value that is consistent with the alternative hypothesis. Okay? So in the lower panel, the assumption is that the alternative, that alpha 1 greater than 0 is true. Okay? We're assuming that it's true. If we want the probability of failing to reject the null when the null is false, okay, we're looking at the probability of failing to reject the null when the alternative is true. Okay? So two things have to happen here. One is that the alternative has to be true. It is by virtue of how we've drawn this distribution and centered it on 2. Secondly, we have to do what? We have to fail to reject the null, which means that we're looking at drawing an alpha hat over this region right here. The probability of that happening, that is to say, failing to reject the null when the null is false, is given by the area under this distribution. Okay? The question now is, once we've got that set up, why don't we arbitrarily shrink the probability of a type 1 error to some smaller level, 0.01, 0.0001, etc.? What would that mean if we were to shrink the probability of a type 1 error to 0.01? It would mean moving this line to the right, okay? So that the area under the top distribution's curve would be smaller. Okay, so here is the probability of rejecting the null when the null is true that might equal 0.025. Okay, so that's fine. We've reduced the likelihood that we're going to commit a type 1 error. But what's happened on the bottom curve? Okay, so we have this new alpha critical, call it alpha critical 2, which has moved away from alpha critical 1, our fail to reject the null has expanded by this amount. The probability of failing to reject the null when the null is false, okay, is now expanded by this much, and the total amount of that probability, that is the probability of a type 2 error, has grown by this much, okay? So anytime we shrink the probability of a type 1 error, we are necessarily going to expand the probability of a type 2 error. So you're going to want to think, when we conduct hypothesis tests, about what an appropriate probability of a type 1 error might be. And I'm going to encourage you to think about the consequences of being wrong in a type 1 and type 2 sense in selecting that error. Okay? Most of the time in economics, we are testing our pet theory, which basically is reflected for the most part in our alternative hypothesis. So if we reject the null and the null is true, it means we've accepted our pet theory when our pet theory was false. And we're going to want to apply a pretty critical or difficult test to that pet theory. And so you'll see in economics and social science probabilities of type 1 errors that are 0.05, 0.025, 0.01. They're quite small. And in setting them quite small, we are applying a more rigorous or difficult test to our pet theory. The consequence of that, though, is that we are expanding the likelihood of committing that type 2 error. Okay? Sometimes there are policy consequences associated with the conclusions that we reach from our hypothesis test. And so we may want to think about what the policy consequences are from being wrong in a type 1 or type 2 sense.